All right, this lesson's on power generation and transmission. And when looking at objective 3 from our overview document, we're really going to focus on just the first sub-objective. We're explaining the operation of basic AC generator and including the effect of changing the generator frequency. So going back to what we learned previous classes with Faraday's law and Lenz's law, we're going to use that to help us here, mostly Faraday's law. Before, we learned that magnetic flux is equal to B times A. And you actually, if you look in your data booklet, there's something else that is occurring here. We, for the most part, have just assumed that the magnetic field lines and the area that it's passing through are perpendicular to each other. So that isn't always the case, especially when we have like a rotating coil, which is what is inside of a generator. So we have to start looking at how much flux is actually passing through that area. So here's an example. We have an angle, we have a magnetic field, and it's traveling at some angle to the area. So we want to find the amount of field lines that are passing through some perpendicular component. So we want to take those field lines and find this component right here. You can imagine the field lines passing through an area similar to how rain hits like your windshield. So if you were to, or even your hand, if it's raining and you put out your hand flat, open face, facing upward, you're going to get hit by all that rain, by the maximum amount of rain. But if you turn your hand so that it's vertical, like it's going up and down, you're going to hit less rain, and depending on how thick your hand is, you are going to feel possibly the minimal amount of rain possible. So then you would, in this situation, would feel the least amount of magnetic flux as well. So the maximum magnetic flux is when it's perfectly perpendicular, and minimum when it's perfectly parallel. So we're going to now add something to this, and it's actually a cosine theta. Where theta is the angle between the B field lines and the normal to the area. As shown in the picture, see how the angle is not this angle, right? It's not that angle. And that's something that you're going to have to be aware of. So this cosine theta, you just recognize that you are looking at the component that is perpendicular to the area, the component of the magnetic field that is perpendicular to the area. And here's an example of the rotating coil, but I really want to go over here and look at how to identify the magnetic flux at each point. So let's look at like flux right here, right? And this is equal to, well, I have BA cosine, and where's our angle, right? So our angle is the angle between the perpendicular, the normal to the plane, and the field line. So if I were to draw field lines going like this, that and our perpendicular to the plane is right here. So that is an angle of 0. And an angle of 0, that gives you your maximum magnetic flux, as shown by this area that in the effective area. And then as it turns, you can see there's less area passing, that the magnetic field lines are passing through. And let's just say that angle's like 45 degrees. So this is like BA cosine of 45, which we know is less than BA. That's all we need. And then when we have something that's perfectly parallel, right? We know that this is our normal, and our magnetic field lines are passing, between here and here. So that's going to be a right angle. So this is going to be BA cosine of 90, which is 0. And this is also shown by this image where there's no effective area, no magnetic field lines are passing through this, there's no magnetic flux. This next one is going to be a little different, and so I'm going to pause and go back to the first picture and show what we have to look at in order to make sense of the next calculation. So right now, it's rotating. I'm identifying that the top of this is purple. Let's say it's the purple side, and it's rotating around. And so for the first two pictures, the North Pole is entering the same side of this coil or loop, and therefore there's the same magnetic flux direction. But right here, it changes direction. It becomes 0, and then all of a sudden, it's entering the opposite side in these last two pictures. So that is going to inform us that this magnetic flux actually becomes kind of negative. It changes direction. That's due to, if we look at Lenz's law, the direction of the current is going to be different depending on this change of magnetic flux, right? So this is actually, even though it's still BA cosine 30, one thing I want to say though is it should be less than 0 and BA cosine 30 in this case is also like it's the magnitude of this is going to be less than BA. So similar to before, we just now know that it's less than 0 as well. This last moment looks like it's very similar to the first one, but in this one we have the purple side right here, the purple side right here, but on these last two, the purple side's on the bottom. So we're going to actually have BA cosine of 0, but in this case, it's going to be negative BA. So it goes BA less than BA 0, less than 0, and the magnitude is less than this amplitude. And then it becomes negative BA. And as it goes back around, it's going to come back and do some process and end up back here once it rotates. If this rotation has constant angular velocity, then this is just a cosine graph with an amplitude of BA. So I want to look at this. Here's another picture that kind of shows how the sides change from top to bottom, and then it rotates back around. So let's identify what graph this would look like. Well, if we knew what BA was, we can say that the amplitude is BA here and negative BA here. And I said it is just a cosine graph. So when we're right here, we have the maximum flux as shown by this picture at 0 degrees. And then at some point in time at 90 degrees, it becomes 0. At 180 degrees, it becomes a maximum, but in the opposite direction, so it's negative. And then at 270 degrees, it's back to 0. And then at 360 degrees, we have made one full rotation, and we're back to the top. And this is just a sine graph or cosine graph. So looks like not great. Yeah, something like that. So if that is our cosine graph, right, this goes here, that connects to right there, that connects to right there, that connects to right there, and that connects to right there. So similarly, I'm going to look down and say, well, what does it look like when I get to the EMF? Well, we know Faraday's law and Lenz's law tells us that, move this away, more videos, explanation of AC current and generator examples. But Faraday's law and Lenz's law states that the EMF is equal to the negative n delta phi over delta t. And this is the part we want to look at. That and this. The n is just a factor. So delta phi over delta t, hey, that's a rate of change. That's a slope. And then negative, oh, it's the negative slope. So when we translate this graph, we have to look at when the graph has 0, and those is what I like to look at first. And I say I can look down and say, you know what, those are zeros. And again, you know what we're doing? We're doing derivations, right? So we're finding the derivative of this magnetic flux, and then the negative derivative. Let's see, we have a negative slope right here, right? And we have a positive slope right here. But because of the negative in the equation, we're actually going to say this is positive, and I'm going to put a point right there. And then that has a positive slope, but due to the negative in Lenz's law, that's going to become a negative maximum. And there's a reason why I'm only going halfway up. We'll see that in a little bit. Oh, my zeros are gone. So this is, let's call this like our maximum voltage and our negative maximum voltage. And this is just going to be a sine graph. And so we have a sine graph of voltage, which is kind of weird. We have positive voltage, negative voltage. This is going to produce what's called an alternating current. So this is like an alternating EMF, which is going to produce an alternating current. An alternating current still travels electrons, still pushes electrons. It just pushes it back and forth. So as the electrons are going back and forth, they still have kinetic energy. The electricity is still transferring. It's just transferring in this oscillating rate, which in order to calculate the actual like voltage we get out of that or current we get out of that, we're going to deal with that next class, so don't worry about the math in that. We're just looking at it conceptually. How does a generator work? How do we get alternating current, and what does that mean? So as we move forward, let's now assume the coil is rotating at twice the frequency of the original rotational speed. So twice the angular frequency, that means it's passing through twice as fast, so twice the angular velocity. And that means that we should not see just one wavelength, but two wavelengths in this magnetic flux. So let's redraw a new magnetic flux. And again, the y-axis is arbitrary in this point. And I already have some black dots here, so I start off here. But instead of reaching 0 at pi over 2, I'm going to reach the negative because it's happening twice as fast. And then it goes up, reaches a maximum, and then a negative. So this is going to be still a cosine graph, just two wavelengths full of a cosine graph. And when we compare these two magnetic flux graphs, what is different that's going to affect our EMF? Because we look at slopes, and because we've crunched one wavelength into two, these slopes had to have increased, and they've increased actually by double. So we should end up with twice the voltage. And so now I will actually say, oh, sorry, not BA, V naught has now doubled. And so that's why I made it halfway in this one. So it's going to be double in this one. So it still starts off at 0, has 0. So it doubles the voltage, but also still doubles the frequency. So it still is two wavelengths full. So we have a 0, we have a 0, and we have a 0. All right, those are all zeros. So we have a maximum. Let's see, this is a negative, this is a positive, this is a negative, this is a positive. But because it switches, this is actually a maximum right here, right in the middle. Yeah. And then a negative here, and then a maximum, and then negative. And we end up with a graph that looks like this. And that's it. That's all we need to do today. So we used our understanding of magnetic field and magnetic flux to identify that there's actually a cosine in this magnetic flux equation, because we want to look at the perpendicular component of the magnetic field passing through an area. When we apply that to a situation where we have a coil or a loop that's rotating in a magnetic field, we're going to find that it actually creates this alternating magnetic flux between a positive BA and a negative BA, and then back to a positive BA, and it just goes back and forth, which means we end up with a cosine graph, or rather just a sinusoidal graph of magnetic flux. We want to find the rate of change of magnetic flux to get to an EMF, and specifically the negative rate of change. So we need to find when the magnetic flux is at maximum, at changing the most, and we end up with a sine graph if we had a cosine magnetic flux graph. And that tells us there's an alternating EMF and therefore an alternating current, which still produces electricity. In fact, every outlet you see in your house has alternating current in it. It's not until after you plug it in, say like a lamp, that uses direct current. Or, you know, if you're charging your phone, you might not want alternating current. You want a direct current to kind of, increase the storage, the energy storage of your battery. And next we found that, hey, when a coil or a loop rotates faster or has higher frequency, then it's going to have sharper changes in magnetic flux, and therefore it's going to have more voltage applied, more maximum voltage applied in an alternating way. And it still keeps, so it doubles the frequency, so it shortens the time period, and it increases the maximum voltage. So note, doubles max voltage. And it still doubles the frequency, right? As it's said here. Okay, and before I leave you, I want to give you some examples of these generators. These generators are the same generators inside of fossil fuel power plants, inside of nuclear power plants, inside of hydroelectric power plants, inside of wind turbines. All of these use this type of generation to produce alternating current. An example is what we've seen, but here's a nice, and I'm going to make sure you can see it, a nice like animation of it, in which you can see that the current is going back and forth. Also, there's other types of generators. This is one where there's a magnet rotating around a inside of like one loop, or if it would be a coil. This is another way of showing AC generation, and we can even go further, and I think they show a lot of different types. So if you want to see all these different types of generators, please click the links on my OneNote. And yeah, get started on the guided practice, and I'll see you in class.